Isomap Principal Component Analysis (PCA), which we discussed in section 6.3, works when the data lies in the linear subspace. However, this may not hold in many applications. Take, for example, face recognition, where a face is represented as a two-dimensional, say 100 by 100 image. In this case, each face is a point in a 10,000 dimensions. Now let us say that we take a series of pictures as a person slowly rotates his or her head from right to left. The sequence of face images we capture follows a trajectory in the 10,000 dimensional space, and this is not linear. Now consider the faces of many people. The trajectories of all their faces as they rotate their faces define a manifold in the 10,000 dimensional space, and this is what we want to model. The similarity between two faces cannot simply be written in terms of the sum of the pixel differences, and hence Euclidean distance is not a good metric. It may even be the case that images of two different people with the same pose have smaller Euclidean distance between them than images of two different poses of the same person. This is not what we want. What should count is the distance along the manifold, which is called the geodesic distance. Isometric feature mapping (Isomap) by Tenable, De Silva, and Lanford in 2000 estimates this distance and applies a multidimensional scaling (MDS) section 6.5, using it for dimensionality reduction. Isomap uses the geodesic distances between all pairs of data points. For neighboring points that are close in the input space, Euclidean distance can be used. For small changes in pose, the manifold is locally linear. For faraway points, geodesic distance is approximately by the sum of the distances between the points along the way over the manifold. This is done by defining a graph whose nodes correspond to the n data points and whose edges connect the neighboring points, those with distance less than some epsilon, or one of the n nodes with weights corresponding to Euclidean distances. The geodesic distance between any two points is calculated as the length of the shortest path between the corresponding two nodes. For two points that are not close by, we need to hop over a number of intermediate points along the way, and therefore the distance will be the distance along the manifold approximated as the sum of local Euclidean distances. See figure 6.9. 6.9 is geodesic distance is calculated along the manifold as opposed to the Euclidean distance that does not use this information. After multidimensional scaling, these two instances from two classes will be mapped to faraway positions in the new space, so they are close in the original space. Two nodes R and S are connected if r x to the r minus x to the s, the distance, is less than epsilon, while making sure that the graph is connected. Or if x to the s is one of the n neighbors of x to the r, while making sure that the distance matrix is symmetric. And we set the h length to the distance between x to the r minus x to the s. For any two nodes r and s, drs is the length of the shortest path between them. We then apply MDS on DRS to reduce dimensionality to k by observing the proportion of variance explained. This will have the effect of placing R and S that are far apart in the geodesic space, or so far in the new k-dimensional space even if they are close in terms of Euclidean distance, in the original d-dimensional space. It is clear that the graph distances provide a better approximation as the number of points increases, though there is the trade-off of longer execution time. If time is critical, one can subsample and use a subset of landmark points to make the algorithm faster. The parameter epsilon needs to be carefully tuned. If it is too small, there may be more than one connected component, and if it is too large, shortcut edges may be added that corrupt the low-dimensional embedding. One problem with Isomap and as with MDS is that it places the endpoints in a low-dimensional space, but it does not learn a general mapping function that will allow mapping a new test point. The new point should be added to the dataset, and the whole algorithm needs to be run once more using n+1 instances.